Good morning and welcome to Open Research Institute's FPGA stand-up for 12th of December, 2023. So the first thing we'll do is a roundtable stand-up. This is what you've done over the past week, what you have planned over the next week or next time period scheduled, and if you need any resources and if you have any roadblocks. So go ahead, Paul.
Well, this week we've been working on trying to get the radio to work on the ADRV 9009 configuration, and it's been a little bit bulky. Things went sideways for a while. We couldn't figure out how to get stuff to build, and it turned out to be kernels had changed out from under us. So we figured out how to nail down a particular commit on the kernel instead of trying to use the constantly changing release version that's supposed to be compatible. That used up a good chunk of the time that we spent this week working on stuff. So that's about the news. Nothing going on in the remote lab that's new.
Okay, thank you. Yeah, things seem to be working. I think, has there been any updates to the utilities for accessing the remote equipment?
Not since the last time we talked, I don't think. The last thing I can think of is that the streaming video is in place now for you to watch the spectrum analyzer remotely. It's an improved facility that we already had, but now it is more efficient, works better. The instructions for how to do that are in the repo, replacing the old version of the document. It has some name like ESA video in the remote lab section of the repo.
Okay, thank you. Yeah, that's been of interest from at least one university, so I thought I'd inquire. All right, and Ken, you have the floor.
Yeah, I've been working on the Theseus cores, just kind of inspecting the core, the code generation at a deeper level, just trying to understand the flow a bit more, tracing signals in simulation, trying to understand. I'm looking for a binary parser. Tried a couple different routes to just look at the source files, but it seems like the test bench throws it onto the ASI bus. I can take it from there. I'll just take it as a given that the inputs are what we want there, and I'm trying to trace from there, going through the input buffers and looking at the filter outputs and the FHT outputs or FFT outputs, just to try and get a rough sense of that the flow is correct. So haven't been able, the goal kind of was to be able to sweep a tone across the different channels. But it looks like at least based on the file description, the inputs may be already doing that. So I just need to first thing, look at the sim that we have in more detail. That's about it.
You mentioned that I think the output of the Theseus cores was all of the channels. Do you want to talk about that a little bit?
Well, it's, it includes the FFT output. So it's in Fred Harris's book, there's the polyphase filter, and then there's the follow-on FFT, which splits it into separate frequency bins. And so the Theseus course includes that. So just looking at how the order of, I think I understand how the order is coming out. It's basically per channel and then within the channel. But trying to understand how that would map into, a software-based. Right now, the reference design for the analog devices just basically wires samples straight through. So if we embed this kind of in line with that flow, we'll get the channel outputs flowing into the into the ARM memory. And so how it would present itself, you know, for a single user is the first thing, and then identifying how we would work with those samples. You know, ultimately, we're going to have to put some additional hardware in there to do the FSK demodulation and some of the downstream operations from that, because we can't, for 64 channels, support that on the ARM. So I guess the hope is get it working with a single channel in software and not require anything beyond the polyphase output to support that. But then from that point, we identify how to augment that with hardware. So that'll be the focus coming up here too. Is that what you were asking? I think it was. Yeah.
Yeah, thank you. Okay, so I think that's a pretty good sort of introduction to the over-the-air status for for the big transponder that we have. What we're doing in the lab right now, or what we've got back to doing after the interesting excursion through some kernel bugs, was the cyclic buffer push is working. Now, this is not flexible enough for like a 4-area MFSK or anything else. What a cyclic buffer push does is you set up one buffer and then you push it once and then it's replayed over and over again. It's a 1024 by 1024 fixed buffer. What we've put into this buffer is a tone, a sine wave, and we picked a frequency and we guessed, educated guess on like, okay, so what frequency will the tone be if we understand the clocks in this SoC? And it turns out we do. So we do have that working. And we did find out that we have a frequency error of about, I think it's 6 or 6.45 kilohertz at 2.5 gigahertz. So that's in Slack. We talked about it a bit. So the next thing is to figure out the non-cyclic buffer. So buffers are updated and pushed out from a source. We're talking about sending a file to the station, pre-computed IQ samples for either the wiggle demo or actually ambient voice. And with the non-cyclic buffer pushes that we've done already, where we're just calculating something and sending it out, we have seen some time gaps. And this is a problem that crops up pretty routinely for people doing this sort of work, and it's addressed at Engineer Zone. Another thing that we've done is we've loaded up the profile. So this SoC, the ADRV 9009 RFIC, the chip, the 9009, it requires a profile to be loaded. You can either load that profile as a text file directly into the file system, or you include all of the values from the many values that are set directly into the device tree. And you can do that through IIO. And there's at least 2 other methods to get the information into the chip. So it's either done built in or it's done at runtime. We have achieved loading up a profile without any fatal errors, but we do get a receive and transmit buffer, I think it's an underrun. This is probably due to not quite having the clocks understood yet and setting all of the different clocks and rates. But we do have some good documentation that we see crop up over and over again on Engineer Zone from Travis and others. And so we just need to comb through it and make sure that we know what we're doing. We are running the ADRV 9009 at a pretty low rate for this sort of work. So we are kind of operating at the edge, and that's going to be something that we need to look at. We also found out there's a really cool tool. There's a GESD viewer, and it gives you sort of a live view into some of the clocks. It's from the point of view of GESD 204B interface, but it's a pretty good indication of whether or not your profile has took. And so that's kind of the over-the-air status. So we're moving from like the simple cyclic buffer into the non-cyclic buffer pushes and hooking it up to data stream. And since we have already demonstrated this over the air with other embedded processors, we do have a good data stream. We know what we're going to send out over the air. We just have to get all the little tubes and wires hooked up correctly. And so Paul mentioned the bug in the Petalinux, and this took about 3 days total. So we included kind of a how-to for addressing bugs in Petalinux. So if there's a bug in the Linux, this boils down to we're dealing with a branch of Linux from analog devices that is actually under active development. So the 2022.2 branch is what we're dealing with. It's not a release, it's still under active development. And there was a bug that was introduced inadvertently, and it tripped us up. So we first kind of thought it's our fault, and then dug into it. We learned a lot, and the way around this is to figure out, essentially roll your development back to the commit that doesn't cause the problem. And there is a way in Petalinux to freeze your commit or to freeze your build, to configure your build to only look at either a particular branch. Now, in our case, that wouldn't work because the active development on the branch introduced the bug, but we identified the commit, and we learned how to cherry pick that particular commit in Petalinux. It's the Petalinux-dev tool. You modify a particular recipe. In our case, it was Linux Xilinx or XLNX. And this worked. Since then, if we'd waited a little bit longer, they would have noticed. In fact, it's probably due to issues filed by other people that also ran across this bug, and we added some comments. So we increased the noise level for this particular bug, and it got attention and it got resolved. So you can see the sort of the development of this bug, how it rose up in the Linux code base over at ADI, starting right after the 30th of November. And so our decision was to roll back to the 29th or previous. So we learned a lot, and the problem got fixed. So best possible outcome. Kind of a steep learning curve for some of us, but good to know. And it's the lessons learned have been documented in the repo. Next up, what Paul's been working on this is GPIO integration. So being able to manipulate GPIOs is a sort of a time-honored Hello World level hardware function. We have a lot of GPIOs on our dev boards, and now is the time to start figuring out how to use them. And dealing with them is not exactly as straightforward as some other embedded platforms. So there is progress. There's at least 3 methods of actuating the GPIOs. And we're looking to demonstrate control of this hardware more fully by the next week. One of the things that I did in the rebuild of Petalinux was to include the GPIO demo application. And that's in there, but it's a very low level, like sysfs way of dealing with the GPIOs. And it's a general application, maybe not as specific or as particular to our needs as it first seemed. So just out of the box, it's just the tools to allow you to manipulate the GPIOs. You still have to know an awful lot of additional things. So I'm looking forward to like being able to write up the guide that we couldn't easily find. If you're watching this and you know of a really good guide, we have a couple like listed off in Slack that we're using. There's a pretty good one on Hackster or hackaday.io. So Hackaday site does have a pretty good one. If you know of any others, please put it in the comments. And then there's been a lot of ESA, European Space Agency activity progress. So we are AMSAT Canada Geotechnical Working Group member, and we will be publicly recognized as such whenever things launch. So that was some good news. And we contribute regularly to their technical discussions. AMSAT DL Germany is reviewing our technical support package and supposed to get back to me. And JAMSAT is discussing our involvement at their board level based on our inquiry. It turns out several of their members were also aware of the ESA activity progress or proposal. So we've delivered our technical support package and made some proposals. And AMSAT UK said that they were planning to include our work in their proposal. I haven't heard anything back since then, but they said all's good. And AMSAT US, or AMSAT USA, it's not clear how we should address or refer to this organization, since North America probably no longer applicable since AMSAT Canada has been established. We did reach out to them too, but they haven't responded. And that is the summary of all the stuff that I know about. So I'm going to stop the share, and then everyone has the floor for any questions or comments before we close for the week.
Good here. Thank you.
No, thank you. It's very deeply appreciated, all the effort to get things done.
Say a little bit more about why GPIO is of immediate interest. I brought it up because I want to use it for debug. We've got this problem with the mismatch in speed between the processor, which is a relatively low powered ARM computer, and the DSP side of the radio, which is intended to be a huge broadband pipe. This is a chip that's intended for use in cellular base stations and the like, that has a lot of capability for high sample rate performance. As a consequence, it doesn't have much in the way of load rate capabilities. You can't turn the clock down to a speed that's comfortable for the processor to handle. So in trying to find some common ground between the software solution that Ken described and the actual hardware capabilities, we're trying to feed the transmitter, because it's easier to debug a transmitter than a receiver, from the processor. And the first thing that happens is these gaps that Michelle mentioned that you can't keep up with real time. And to find out whether that's your problem or something else is your problem, it's really handy to be able to put out a little pulse every time you do something. And then you can use test equipment to measure the frequency of the pulses and, how much variation in the gap there is. So if I could very easily put out a signal, then I could learn a lot about what's going on in real time in a way that's very difficult to duplicate in pure software. So otherwise you'd have to build some hardware in the FPGA. We're not yet conversant enough that that's easy to do. So hardware and test equipment is what the remote lab is about, and getting hooked up to the software through a GPIO would be a big step forward in the debugability. So that's what we're heading for. And GPIOs are easy, but sometimes they're easier than others. And the fact that we know how to change a GPIO is part of the solution. The other part of the solution that we need is knowing which GPIO to wiggle. And if there's an easy to follow map of where the GPIOs are on this development platform, we haven't found it yet. So in fact, I have yet to be able to actually light up an LED or wiggle a GPIO, because I don't know where to go in the address map for it. So that's a little bit more detail on where we are on the GPIO.
Yeah, thank you. I concur. We'll keep at it and we'll write down anything that we find out. Try to make it as accessible as possible to anybody that's in the same boat. Excellent. All right, thanks everybody. I think the other thing that we talked about was how to back up our work and get it archived. At the application layer, we're using a lot of different tools, including Vitis from Xilinx, and the Vitis project can be exported into a zip file. There also, since Vitis is essentially Eclipse, there is GitHub or Git integration inside of Vitis, and so last Thursday, Anshul requested, to get this working so that it could be backed up to our GitHub. So the first effort resulted in a catastrophic disagreement between the local repository in Vitis on ChocoCat and the target repository on GitHub. And there was lots of remarkable errors that I've never seen before, and it looked like it was not recoverable. So at some point I bricked it. So we backed up. I made an export, just an ordinary export of the project to a zip file, and I posted it for Anshul to test because it's like, okay, this is the content that will be backed up with this GitHub or Git integration. Is this useful to you? Can you take this zip file, open this project, and then operate our station from your account on ChocoCat? So once that seems to be clear, I mean, that would be a big step forward than just simply sharing the C code. So right now, all we do is like capture the actual source code file. And that honestly is not enough because a lot of the configuration and the platform itself can be, you can take a snapshot of everything, the platform, the system, and the application. All of that requires kind of a lot of work. We have it documented, but it would be really great if somebody that already has an account, at Remote Labs could just simply open it and operate the hardware just from that point. That's kind of the goal. So if it has to be done with a zip file and an export, that's okay. That's a big step forward. Even better would be being able to just clone a repo and have it just magically show up. So either one of those is probably going to be what we do going forward, and we will move past just sharing C code file and letting you set up your own environment. So yeah, that's the summary on that. And I think that might be it. We're going to steam forward on the GPIOs. We're going to try to get a full featured and non-cyclic transmitter working. And you know what if that's I mean, those are big steps right there. We're on the Theseus cores side. We're looking at the things that Ken's talking about, and also we do have our document that we started on like, here's how we've integrated our work in the past into the reference design. We're looking at and actively thinking about how to get the Theseus cores into the reference design, with all the buffers set up. So there's plenty going on. And if you're listening to this and interested in getting involved, you're welcome. And my job is here to help it make it as accessible and fun and rewarding as possible. So get in touch. All right, thank you, everybody. And we'll see you next Tuesday if all goes well. That'll be the 19th of December, and then we'll probably take a break after that until the new year. All right, see you soon.